Path of a reaction and the effect of a catalyst. So the equilibrium constant tells us how far the reaction goes, whether we have a lot of product or a lot of reactant, but doesn't tell us how fast it gets there. The reaction rate is what tells us how fast it's going to get there. There's something called activation energy. It's like a barrier to the reaction. It's an energy barrier that needs to be overcome in order for the reactants to be converted into products. And usually what this amounts to is the fact that in order for you to make the products, there are bonds in the reactants that have to be broken. So you have to break some bonds before you can make new ones. And even if it's energetically favorable, there's still this initial investment of energy to break the bonds. If nobody's willing to invest in breaking those bonds to get the payoff of making the new ones, then nothing's going to happen. So we can look at graphs like this. So here on the y-axis is energy going up to the top, and here's the reaction pathway. You could think of this as time. So here we've got our reactants. Here we're reacting hydrogen and oxygen to form water. In order for these guys to react, the bonds have to be broken. Here's this hydrogen molecule, there's a bond. It takes some force to pull those two hydrogen atoms apart. And we have to break this one, and then the oxygen bond has to be broken as well. So there's some energy that needs to be put in. So the energy of the reactants is here. In order to get them to react, we have to increase their energy until they have enough energy that those bonds can get broken. And once we get to that point, whew, down the hill. Easy. It's a little bit like going down a slide, you know. You have to climb up the ladder to go down. There's no shortcut here. So we have to go up and over. It's a little bit, this diagram always reminds me of playing miniature golf. Right? This, if it was green maybe. This looks like one of those humps in the miniature golf course, right? And so here you've got your little golf ball, and you have to hit it with enough energy that it goes up and over the hump, right? Because sometimes what happens is you hit it and it goes up here and it comes back down, right? You're like, oh man, gotta hit it harder next time. You hit it harder and it goes, oh, and it teeters and it comes back down, right? It has to have enough energy. And this goes back to collision theory as well, where those molecules have to collide with enough energy for them to actually react. If they just bump gently into each other, a reaction's not going to occur. We have to have enough energy to break those initial bonds. Once we break those bonds, it's all downhill from there. And creating the new bonds gives off a lot of energy. Any questions? Does that make any sense? So, is there any way we can speed up a slow reaction? If that hump is high, the reaction is going to be slow because we don't have enough particles having collisions with high enough energy. Yeah, there are ways we can speed up a slow reaction. So the higher the activation energy, the fewer the number of reactant molecules that make it over the barrier, right? In general, at a given temperature, the higher the activation energy, the slower the reaction rate. Well, what if we increase the concentrations of the reactants? That's going to increase the number of collisions per unit of time, and there's a range of energies in those collisions. If we just have more collisions, we're going to have more that have enough energy. So that will speed it up. What if we increase the temperature? Increasing the temperature increases the kinetic energy of the particles. Temperature is a measure of the average kinetic energy. So if we increase the kinetic energy, now we're going to be increasing the energy of those collisions, and so more of them are going to get over. So if we go back to the miniature golf, increasing the concentration is like just hitting more and more balls over. not really doing anything to your swing, but just kind of randomly hitting balls over, you're going to get more over, right? Increasing the temperature means that you're going to hit them all harder. And now definitely more of them are going to go over. The other thing we can do is to use a catalyst. And a catalyst provides an alternate pathway. It lowers the activation energy. What if we cut off the top of that hump? Would more of the balls go over? Sure they would, right? And sometimes, there's situations in life where, man, if we could just cut that down and we could just jump over it, so much easier. You're doing high hurdles. Could we just lower the hurdles? It'd be so much easier, right? Well, a catalyst lowers the hump. So the author of this book used boulders going over hill. I like the miniature golf better. So you're rolling boulders up this hill. Why would you do that? Of course, then, really, why do you play miniature golf? I don't have an answer for that one. Anyway, so without the catalyst, these boulders have to go way up this steep hill, and it's going to be a slow reaction. With a catalyst, now I don't particularly like this illustration, now we've got this alternate pathway. I think I talked about, did I tell you about the kindergarten children going over the fence with the teacher? No? Okay. No, I think I would have remembered that. Okay. So, again, but it could happen. It's less far-fetched than, So here are the little kindergartners, and for some reason, they need to get over this fence. Perhaps there's a fire at the winery next door to their school. That really happened to my kids. The winery next door caught on fire. They didn't have to climb over a fence, but we'll just say that the children, to escape, they have to climb over the fence. So here's these little kindergartners, and they need to climb over this fence. Now, can they do that? Sure. But it requires a fair amount of energy for them, and it's going to be kind of slow, right? So this is the reaction, and this is the reaction, the energy barrier, the activation energy, this fence. Well, what if we had a teacher here acting as a catalyst, and as the kids ran up here, she lifted them up and handed them over the fence? Would that go faster? Probably so. And that's what a catalyst is like. A catalyst makes the reaction faster, but it doesn't get used up. It's not actually a reactant. There's one teacher here, and she can catalyze many students getting over the fence. Another way to speed this up would be to lower the fence, right? What if we drop out a couple of bars of the fence there, and they just have to go over the bottom one, lowering the activation energy? This is also going to get them over faster. Does that make sense? Increasing concentration would be increasing the number of kindergartners. If you doubled the number of kindergartners, the rate that they go over the fence would get faster just because there's more of them. And increasing the temperature, I guess, would be like feeding them rock stars. And they get all hepped up. Maybe they don't even need that. Probably just a couple of cupcakes would do it. Get them all hyped up in high energy, and then they'll go over the fence faster. So the catalyst provides an alternate pathway. So our more scientific diagram here. So this was the original activation energy. Had to get over this big energy hump. But with the catalyst, it lowers the hump. It provides a pathway that requires less energy. And so more of the reactants can react to form the products. The reaction speeds up. And this whole idea of a catalyst is a really important concept. There are biological catalysts. We call them enzymes. One way to speed up a reaction is to increase the temperature, because then more kinetic energy, more of them have enough energy to get over the hump. You have, probably 50 gazillion chemical reactions going on in your body right now. Some of them occur very slowly at room temperature. Does your body just heat it up to 150 degrees Celsius to get that reaction to go? No, because that would destroy the reactants and products. Okay, a lot of the reactants and products in your body are thermally sensitive. I mean, what happens to an egg when you stick it in boiling water? It cooks, right? It gets all hard. It was liquid before. The heat denatures the proteins, and that's what it would do to your body as well. So your body cannot use temperature to increase the rate of reactions. And it can't really use increased concentration effectively either. And so what it does is it uses enzymes as catalysts. So many of the reactions that are needed for your body to live are too slow at normal temperatures. And so your body uses enzymes to increase the rates of these biochemical reactions so that they're fast enough for you to remain alive. An example here, this is sucrose. This is a disaccharide. It's glucose and fructose molecules that are bonded together. And your body needs to metabolize that and break it into glucose and fructose. Well, there's an activation energy for that. At room temperature, this happens, or even at your body temperature, 37 degrees Celsius, that happens very slowly because there's a high activation energy. But there's an enzyme called sucrase that catalyzes that reaction. It's like the teacher helping the kids over the fence. So we don't need to give them sugar, and we don't need to just get a whole bunch more of them so that we can get some over the fence. We've got the teacher there, and she's going to lift them over. So sucrase is the catalyst, and it lowers the activation energy so that more of the sucrose molecules can be metabolized into glucose and fructose. And just kind of an overview of how this works. So here's, just some representation of sucrase. And these enzymes are big, complicated proteins generally, but they have an active site. And it's a little bit like a docking station for a spaceship. Okay, and so sucrose comes in here, and this place is just right for it to fit in. And it comes in and docks in this active site. And when it fits into this active site, it gets stretched a little bit, and so this bond that's holding those two pieces together is weakened because there's some tension on it. And so it's much easier for that to break. And then when that breaks, the sucrase says, okay, done with you, go on your merry way. And it leaves, and then the active site is available for another sucrose molecule to come in. It comes in, and it fits in just all nice and snug in that active site, and then it gets stretched a little bit, and then it's easier to break that bond, and it goes on. Any questions? I'm also teaching biochemistry right now, and this is one of my favorite topics. And there's the end of the chapter.